Problem number 3 on beams. See, for the beam fixed at both ends and load as shown in the figure, determine the displacement and slope at node 2 and reaction at node 1 only. See, this is the figure given. See, it is a fixed beam and is subjected to a 10 kilonewton concentrated load at the center of the beam and a moment, anti-clockwise moment of 20 kilonewton meter is acting at the center of the beam. The length of the beam is given, it is 6 meter. See here, the moment of inertia of the beam is not given, but the cross-sectional area of the beam is given. From this you can find out the moment of inertia. See, this problem has appeared in the VT question paper in the year December 2015, January 2016. See here, you have to find out the displacement and slope at node 2 and reaction at node 1 only. See here, node numbering they have already given, node 1, 2, 3. Here you have to find out the displacement and the slope at node 2 and the support reaction at node 1. Support reaction at node 3 is not required. You have to calculate only the support reaction at node number 1. Now we will see the solution. First we will calculate moment of inertia. See, moment of inertia I is equal to, for rectangle cross section it is BH cube by 12. See here, B is 0.3 meter and H is 0.2 meter. So it is 0.3 into 0.2 cube divided by 12. We will get 2 into 10 power minus 4 meter to the power of 4. This is moment of inertia. Next is the finite element model, FE model. FE model. See here, already they have given the node number 1, 2, 3. Means we have to use 2 1D beam element for finite element model. This is element number 1. This is element number 2. Node numbering 1, 2, 3. Next is the nodal displacements. At 1 we will take Q1 as translation, Q2 as rotation or slope. At node number 2, Q3, Q4. Similarly, at node number 3, it is Q5, Q6. And the nodal forces and nodal moments. At node 1, F1 is the nodal force and M1 is the nodal moment. Similarly, at node number 2, F2 is the nodal force and M2 is the nodal moment. At node number 3, it is F3 and M3. Length of the element is 3 meter each. See here, one more thing. The Young's modulus of the material is not given. So we will assume E is equal to 200 gigapascal. See the model here, length is in meter, so you have to take all the values in meter only. It means you have to take Young's modulus in Newton per meter square. Similarly, moment of inertia in meter to the power of 4. Next is elemental stiffness matrix. Formula is K is equal to EI by L cube 12 6L minus 12 6L. 6L minus 12 6L 4L square minus 6L 2L square minus 6L 2L square 12 minus 6L minus 6L 4L square. This is the formula for elemental stiffness matrix. Next we will calculate the elemental stiffness matrix for element 1. See, for element 1, K1 is E, we have assumed 200 into 10 power 9 into I, it is 2 into 10 power minus 4 divided by L, it is 3 cube 12 6L, it is 18 minus 12 again 6L 18. See, due to symmetry I can write here 18 minus 12 18. 4L square, it is 36 minus 6L, it is minus 18. 2L square, it is 18. Here minus 18 18. Next 12 minus 6L, it is minus 18. Here also minus 18. 4L square is 36. If you simplify this, we will get K1 is equal to 148 into 10 power 3 12 18 minus 12 18 18 minus 12 18 36 minus 18 18 minus 18 18 12 minus 18 minus 18 36. This is K1. Next is numbering. See the FE model. Element number 1, it connects node number 1 to 2. At node number 1 the DOF is Q1 Q2. At node number 2 the degrees of freedom is Q3 and Q4. Therefore the numbering will be 1 2 3 4. So here the numbering is 1 2 3 4. Here also 1 2 3 4. Next, elemental stiffness matrix for element 2. For element 2, see here for both the elements lengths are same, it is 3 meter for both the elements. Also the cross sectional area is same, and also the Young's modulus is also same for both the elements. Therefore the elemental stiffness matrix of first element will be equal to second element. Therefore here you can directly write for element 2, K2 is 1481.48 into 10 power 3 12 18 minus 12 18 18 minus 12 18 36 minus 18 18 minus 18 18 12 minus 18 minus 18 36. This is for second element. Next is node numbering. See the FE model. Element number 2, it connects node number 2 and 3. At node number 2 the degrees of freedom is Q3 Q4, and at 3 it is Q5 Q6. Therefore the numbering will be 3 4 5 6. 3 4 5 6. Here also 3 4, 5, 6. Next is global stiffness matrix. Global stiffness matrix, that is K is K1 plus K2. Now what about the order of the global stiffness matrix? See the FE model here. Here there are 3 nodes. Each node has got 2 degrees of freedom. Means the total degrees of freedom of this finite element model is 6. Therefore the order of the global stiffness matrix will be 6 cross 6. Therefore K is 1481.48 into 10 power 3 outside, numbering 1, 2, 3, 4, 5, 6. Here also it is 1, 2, 3, 4, 5, 6. See, first we need the element corresponding to 1 and 1. See the elemental stiffness matrix of first element. Here the element corresponding to 1 and 1 is 12. In K2 we don't have any element corresponding to 1 and 1. Therefore the element corresponding to 1 and 1 is 12. Next is element corresponding to 2 and 1. See, in K1 the element corresponding to 2 and 1 is 18. But in K2 we don't have any element corresponding to 2 and 1. Therefore element corresponding to 2 and 1 is 18. Next we need element corresponding to 3 and 1. See, in K1 the element corresponding to 3 and 1 is minus 12. But in K2 we don't have any element corresponding to 3 and 1. Therefore the element corresponding to 3 and 1 is minus 12. Next we need element corresponding to 4 and 1. See, in K1 the element corresponding to 4 and 1 is 18. In K2 we don't have any element corresponding to 4 and 1. Therefore the element corresponding to 4 and 1 is 18. Next we need element corresponding to 5 and 1. In K1 we don't have any element corresponding to 5 and 1. Also in K2 we don't have any element corresponding to 5 and 1. Therefore element corresponding to 5 and 1 is 0. We need element corresponding to 6 and 1. See, in K1 we don't have any element corresponding to 6 and 1. Also in K2 we don't have any element corresponding to 6 and 1. Therefore element corresponding to 6 and 1 is 0. Now due to symmetry I can write the first column 18 minus 12 18 0 0. Next we need element corresponding to 2 and 2. See, in K1 the element corresponding to 2 and 2 is 36. But in K2 we don't have any element corresponding to 2 and 2. Therefore element corresponding to 2 and 2 is 36. Next we need element corresponding to 3 and 2. See, K1 here element corresponding to 3 and 2 is minus 18. But in K2 we don't have any element corresponding to 3 and 2. Therefore element corresponding to 3 and 2 is minus 18. Next we need element corresponding to 4 and 2. See, K1 here element corresponding to 4 and 2 is 18. In K2 we don't have any element corresponding to 4 and 2. Therefore element corresponding to 4 and 2 is 18. Next is element corresponding to 5 and 2. See, in K1 we don't have any element corresponding to 5 and 2. Similarly in K2 we don't have any element corresponding to 5 and 2. Therefore element corresponding to 5 and 2 is 0. Next element corresponding to 6 and 2. In K1 no element corresponding to 6 and 2. Similarly in K2 no element corresponding to 6 and 2. Therefore element corresponding to 6 and 2 will be 0. So due to symmetry I can write the second column. It is minus 18 18 0 0. Next is third row, third column, element corresponding to 3 and 3. So here in K1 the element corresponding to 3 and 3 is 12. Also in K2, the element corresponding to 3 and 3 is 12. Therefore, element corresponding to 3 and 3 becomes 12 plus 12, it is 24. Next element corresponding to 4 and 3. See, in K1, element corresponding to 4 and 3 is minus 18. In K2, the element corresponding to 4 and 3 is 18. Therefore, element corresponding to 4 and 3 becomes minus 18 plus 18, it is 0. Next element corresponding to 5 and 3. See, in K1, no element corresponding to 5 and 3. In K2, the element corresponding to 5 and 3 is minus 12. Therefore, here element corresponding to 5 and 3 becomes minus 12. Next element corresponding to 6 and 3. See, in K1, we don't have any element corresponding to 6 and 3. In K2, we have element corresponding to 6 and 3, that is 18. Therefore, here element corresponding to 6 and 3 becomes 18. Now, due to symmetry, we can write the third column. It is 0, minus 12, 18. Next is element corresponding to 4 and 4. Here, if you see K1, the element corresponding to 4 and 4 is 36. Similarly, in K2, the element corresponding to 4 and 4 is 36. Therefore, element corresponding to 4 and 4 becomes 36 plus 36. It is 72. Next element corresponding to 5 and 4. In K1, we don't have any element corresponding to 5 and 4. But in K2, we have element corresponding to 5 and 4, that is minus 18. Therefore, here the element corresponding to 5 and 4 becomes minus 18. Next, we need element corresponding to 6 and 4. In K1, no element corresponding to 6 and 4. But in K2, we have element corresponding to 6 and 4, that is 18. Therefore, here element corresponding to 6 and 4 becomes 18. Next, due to symmetry, we can write the fourth column. It is minus 18 plus 18. Next is element corresponding to 5 and 5. See, in K1, we don't have any element corresponding to 5 and 5. In K2, we have element corresponding to 5 and 5, that is 12. Therefore, here in the global stiffness matrix, the element corresponding to 5 and 5 becomes 12. Next is element corresponding to 6 and 5. In K1, we don't have any element corresponding to 6 and 5. In K2, we have element corresponding to 6 and 5, that is minus 18. Therefore, here it becomes minus 18. So, due to symmetry, we can write the fifth column. It is minus 18. Next element corresponding to 6 and 6. See, in K1, we don't have any element corresponding to 6 and 6. In K2, we have element corresponding to 6 and 6, that is 36. Therefore, here element corresponding to 6 and 6 becomes 36. This is the global stiffness matrix. Next is nodal displacement vector. Nodal displacement vector. It is Q is equal to, at node 1 the displacement is Q1, Q2. At node 2 it is Q3, Q4. At node 3 it is Q5, Q6 transpose. This is the nodal displacement vector. Next is nodal load vector. Nodal load vector, that is F is, at node 1 the nodal force is F1 and nodal moment is M1. Similarly, at node number 2 it is F2, M2. At node number 3 F3, M3 transpose. Or F is, see the figure, node number 1 is fixed, means here we don't have any force and any moment. Therefore, F1 and M1 becomes 0. So here F1 is 0, M1 is 0. Next we need F2, M2. See the figure, at node number 2 we have F2 is equal to 10 kilonewton. Since it is acting downward, we will take minus 10 kilonewton. And the moment, we have a moment at node number 2 that is 20 kilonewton meter anti-clockwise. Here remember the sign convention for applied moment. If the moment is applied in anti-clockwise direction, we will take positive. If it is acting in clockwise direction, then we will take negative. Remember, if the moment is acting in anti-clockwise direction, then it is taken as positive. If it is acting in clockwise direction, then it is taken as negative. Since here the moment is in anti-clockwise direction, we will take M2 is equal to plus 20 kilonewton meter. Therefore, at node number 2, nodal force is minus 10 kilonewton and the nodal moment is 20 kilonewton meter. That is, F2 is minus 10 and M2 is 20 kilonewton meter. So F2 it is minus 10 into 10 power 3. M2 is 20 into 10 power 3 Newton meter. Next we need F3 M3, that is nodal force and moment acting at node number 3. See the figure. Node number 3 is fixed, means there is no force, also no moment is acting. Therefore F3 and M3 becomes 0. So here F3 is 0, also M3 is 0 transpose. This is the load vector or force vector. Next is equilibrium condition. Equilibrium condition, that is K into Q is equal to F. K is 1481.48 into 10 power 3, 12, 18, minus 12, 18, 0, 0, 18, minus 12, 18, 0, 0, 36, minus 18, 18, 0, 0, minus 18, 18, 0, 0, 24, 0, minus 12, 18, 0, minus 12, 18, 72, minus 18, 18, minus 18, 18, 12, minus 18, 36. This is K into Q. It is Q1, Q2, Q3, Q4, Q5, Q6 is equal to F, that is 0, 0, minus 10 into 10 power 3, 20 into 10 power 3, 0, 0. This is the equilibrium equation. Next is applying the boundary condition. Applying the boundary condition. See the figure. Node number 1 is fixed. Also node number 3 is fixed. Therefore the corresponding displacements will be equal to 0. That means at node 1 the displacement is Q1, Q2. At node number 3 it is Q5, Q6. Since node 1 and 3 are fixed, Q1, Q2, Q5, Q6 are 0. So we can write, since node 1 and 3 are fixed, the corresponding displacements Q1 is equal to Q2 is equal to Q5 is equal to Q6 is equal to 0. Now by applying the elimination method, we can eliminate the corresponding rows and columns. So using elimination method, we can eliminate corresponding rows and columns. See, here Q1 is 0, therefore I can eliminate first row, first column in the equilibrium equation. Similarly, Q2 is 0, means I can eliminate second row, second column. Q5 is 0, means I can eliminate fifth row, fifth column. Similarly, Q6 is equal to 0, therefore I can eliminate sixth row, sixth column. So equilibrium equation reduces to 1481.48 into 10 power 3 24 0 0 72 into Q3 Q4 is equal to minus 10 into 10 power 3 20 into 10 power 3. This is the equilibrium equation after applying the boundary condition. Now we will multiply the matrix. We will get 24 Q3 is equal to minus 6.75 into 10 power minus 3. Similarly, 72 into Q4 is equal to 0.0135. Therefore, we will get Q3 is equal to minus 2.8125 into 10 power minus 4 meter. This is Q3, that is the transverse displacement at node number 2. And Q4 is 1.875 into 10 power minus 4 radian. This is slope at node number 2. Next we have to find out the support reaction at node number 1. Support reaction at node 1. See, for a beam at the supports there will be two reactions. One is the reaction force and one more is the reacting moment. Here we will take R1 as reacting force and R2 as reacting moment. Therefore, the reaction force R1 is K11 Q1 plus K12 Q2 plus up to K16 Q6 minus F1. If you substitute all the values and simplify, we will get R1 is equal to 10 kilo Newton. Next R2. R2 is K21 Q1 plus K22 Q2 plus dot up to K26 Q6 minus M1. If you substitute all the values and simplify, we will get R2 is equal to 12.5 kilo Newton meter. This is the reacting moment at node number 1. Thank you.